Hi, this is Dion from FocusChemistry.com. Today we're going to talk about a kinetics question that a lot of students have problems with, and that is called the pseudo-order reactions. If this question was taken out from an old question from Raffles Junior College 2002, and the question is shown on the board. Basically, the reaction is a gas phase reaction between A and B to form a product called A2B2. This question has got some kinetic data in it, and the question asks students to find the orders with respect to A and B. Now let's take a look at the data given to us. We're having a time. There are two experiments conducted, experiment 1, experiment 2, and at different time intervals, every 5 seconds interval, this is in seconds, right? Basically, what was determined was the concentrations of A2B2. These are the concentrations of A2B2. These are the concentrations of A2B2 at two different experiments. Now, notice that if I were to plot this graph, I will get something that looks like this. Now, these two concentrations are the concentrations of A2B2, and this is time. And I'll get, you notice that the numbers are increasing with time for both graphs. So basically, you get two curves like this, one above and one below. And because both reactions are taking samples at the same time intervals, you notice that graph 2, experiment 2, the values are higher than experiment 1. So therefore, experiment 2 is the second graph, the graph that's on top. Experiment 1 is the graph that's below. Right? Now, experiment 1, experiment 2, the difference is the concentrations of B that's used. For A, the concentration is the same. For experiment 1, the concentration of A is found to be 0.12 moles per dm cube. The concentration of B for first experiment is found to be 1.2 moles per dm cube, right? Now for experiment 2, the concentration of A is the same as experiment 1, 0.12 moles per dm cube. But the concentration of B is different. It's 1.8 moles per dm cube, right? So previously, right, if you've come across questions where there's one product curve, let's compare this particular question with a question that goes like this. If there's only one reactant called A to become B, the rate equation is expressed in terms of A in this manner. You'll find that if you have only one graph like this, where I've got the B's concentrations, which is a product, versus time, I get a graph that's like this. It's quite obvious that because there's only one graph, I can use this data to find the order of one reactant. Now we are given two graphs now. It's obviously to find the order for two reactants, A and B, right? But the thing is that what method should we use to find for A? What method should we use to find for B? And this is a problem that a lot of students have. They know how to do this, a single reactant component, single component question, but they have a problem if dealing with product curve and double component. So let's see what happens to this and how should we solve this. Now we take a look at the rate equation. The rate equation is expressed in terms of the two reactants, which is A and B. Right? You take a look, there's A and B as the reactants, and the rate equation is this. Our task now in this question is to solve for A and B's orders, which is M and N. Okay? Now normally when we conduct a kinetics experiment, right, we have to make sure that the rate constant is constant throughout with time. Which means if I were to plot a graph of rate constant with time, it's important to keep it constant with time. Now because if you were to have a rate constant fluctuating with time, and you're going to find a rate constant for a particular reaction, we're not going to find the actual rate constant, we're just going to find an average rate constant. And therefore, whenever you do SPA planning or planning from experiments or kinetic experiments, a very important thing is that the reaction must be at constant temperature. Because if the temperature is not constant, then my rate constant will change with time as the reaction proceeds, and therefore look at this graph. If it changes with time, we cannot find the actual value of K. We're actually going to look at a fluctuating value of K, and if in the end we find a value of K, it's going to be an average value. What we do not want is that. What we want is to have a constant value of K. And therefore, normally for experiments where you're going to plan a kinetics experiment, this is a very important thing all of you got to remember, which is it must be conducted at constant temperature. Now how is that done, constant temperature reactions? It's very simple. If the reaction is endothermic, which means it takes in heat, then basically you must have an external heating source so that the temperature is at constant temperature. If it's exothermic, which it gives out heat, then basically you must have a cooling source to remove the heat. Right? So this is the thing you must take note of. And because of that, when temperature is constant, you find that the rate constant is constant with time. That's important. The conclusion is rate constant is constant with time. All right? The next thing is this. We have two reactants now. And if you notice that the concentration of the reactants, you notice the A's concentration experiment 1 is 0.12, B's concentration experiment 2 is 1.2. You notice that the difference in the concentration is 10 times between A and B. In experiment 2, you find that B is 1.8, A is still 0.12, B is 15 times the concentration of A. You notice in both experiments, one thing that we notice is this important thing, and that's B is in large excess. Large excess means what? That means it is at least 10 times or 15 times or 20 times more than the other reactant's concentration. Now this is a very important thing. Now what happens is that if B is kept in large excess, what we're going to see is that B's concentration is constant with time as well. You may be thinking this is not possible. No. Let me give you an example. If you were to go to a sea, right, which has got infinite volume of water, and you go to the seaside, and basically you have a bucket of fresh water, and you've got a whole ocean of seawater. And let's say you have a mixture, you're going to make a mixture where you have 1 cup of fresh water, and you take out 1 cup from the sea to do a mixture of seawater and fresh water. You notice as time goes on, the percentage change of fresh water is going to be much higher than the percentage change of the volume of the sea, because the sea's volume is infinite. So it looks as if the sea's volume has never changed. In fact, it has, but it's insignificant. The same things apply to this concept. If B is in large excess, right, then B's concentration looks almost constant with time compared to A's concentration. And because B is constant with time and K is also constant with time, we're going to lump these two expressions together, which are constant with time. So I'm going to erase off this for more space. Because both of these are constant with time, we're going to do this now. Because this is large excess now, you find that B's concentration can be lumped together with K's value, and we're going to use K prime to express the product of those two numbers. We're going to express as a new constant called K prime, where K is K, the original K prime is K, the original K, times B to the power of n. Now why we can do that is because K and B are both constant with time, so therefore we can lump together to form a new constant called K prime. Now this rate equation and this rate equation are different. Now this first rate equation is known as a theoretical rate equation. That means that's the actual rate equation. But because of the manipulation of B, our observed, this is called observed now, the observed rate equation is seen to be like this now. So from a two reactant reaction, it becomes as if it's dependent only on one reactant equation or reaction. This is what we so call as a pseudo order reaction. In English, pseudo means apparent. Apparent means it looks like this, but actually it's not like this. Actually it's like this, right? So this is the meaning of pseudo. Pseudo is when what you observe is going to be different from what you actually have in the beginning, have theoretically. Now let's assume that today we do B in large excess, the rate equation becomes like that, right? What happens if the next day you do, let's say we change the question now, A is in large excess. That means you conduct the same experiment, but the concentrations of A and B, we swap it, right? Now A is 1.2, B is 0.12, and likewise for experiment 2. What we're going to see now? We're going to see that A is in large excess, and therefore A's concentration is constant with time. And therefore now the observed rate, right, the observed rate equation becomes a new constant, and B stays in the equation, and the new constant basically is the original rate constant times the concentration of A. Now you notice that now we're lumping A with the original rate constant because A's concentration now doesn't change with time. And therefore you notice one thing is that no matter how you manipulate it, depending on how you manipulate it, the person who does the experiment, the observed rate equation can be very different, right? The observed rate equation can be very different, and therefore we might have different apparent rate constants, but the real rate constants can still be found if you know the apparent rate constant. Now the beauty of this particular process, right, this particular procedure of making one of them in large excess is to reduce from a 2-reactant equation to become a 1-reactant equation. And since it's 1-reactant equation, then this becomes very similar to what we previously saw as a single reactant question. Remember previously just now I was saying that if the reactant is single, like this, A becomes B, and we got only one graph, where this is B's concentration and this is time, we can use this graph to find the order respect to A. So notice that this particular question, you only have one reactant left, your parent rate is due to one reactant left, right? So basically you can choose any graph you want to find the order respect to A. So let's take a look at this question again. You find that the apparent rate equation is dependent on A, it's only one reactant, and therefore we can find the order respect to this limiting reactant by the method of half-life, which is what we're taught in schools, the half-life method. One reactant, if you got a concentration of product versus time, we can find a half-life and therefore prove that the order is 1, right? And that's how this question is solved, right? And that's all I have for you today. The purpose of today's experiment, discussion is just to show you how a reaction ideas can be easily solved using the pseudo-order method. This also is called the method of excess, all right? So this is all I have for you. For more information, come and log on to www.focuschemistry.com. Thank you.